Yeah, I forgot until like 9:30 last night. And it was just like, oh, there's actually
I remember, but I deliberately waited till like 11 to start it.
it wasn't that bad. Is everyone
They thought fall breaks. I'm kidding.
I organized my folder yesterday. Hey Chloe. How are you?
I'm so tired.
Same.
This is what overachieving looks like.
Did you use the internet on the extra credit?
The what?
I used a video and I googled it, and I spelled Googled.
Why did you do that?
What?
What's that for?
You said to write a statement to prove that you didn't look it up, or to write a statement to say that you did look it up. I like the colors. Is it for anyone?
There was a lady in the bathroom listening to the coffee, and I was like, okay. Gotta keep that in mind. I need it one day.
Did you read for Britlet today?
No, I haven't done it. Did you? I will.
During that 4-hour break. Do you have a 4-hour break? Over
No.
Britlet? Oh. I do.
Gosh dang, Brittany.
What classes do you have?
Actually, I do have a few hours. I don't know how many it is because it's not counted and I don't feel like it. But I'll have class till 1:30.
Wait, from here until 1:30? What do you do?
Sometimes I intern. Just sit on the couch.
Just like what you do.
Sometimes I'm productive, but that's a rare occurrence.
I have a raincoat in my car.
Sorry, I don't own a coat. I literally haven't owned a coat in years. I don't get cold enough for a coat. I mean, I don't. Even in the winter, I just don't wear a coat.
Really?
Yeah, I'll just put on like a hoodie.
I
See, I don't freeze.
a hoodie, but I'm like,
I don't own a proper coat.
I'm like this tall, and like the blood doesn't start to like my hands or feet. Maybe.
I get too
I
hot
mean-
too fast. But I've started to
It's not
stop
like I
caring
know what I
about
was
how
doing.
hot I get.
I know that for 43, I want to
It's
go
just
over
not worth
it.
caring about.
Wait, Corey, I think that you can swim.
I feel like I probably just expanded it wrong instead of screwed up somewhere else. For this one, this is the right answer, but that's not what I got. Because, yeah. 43, I know. So, yeah, I'm.
Yeah, that's what I mean.
Yeah, I did it wrong. Oh.
Oh, well. Yeah, it's just,
Yeah. Where does he want the first, start the first goal?
I guess I'll take it.
Is that frozen to quotient?
Yeah. Oh.
Yeah.
I told him, it's just like, I have to get a video.
Yep.
That's what I said too. It's just like the algebra
Are we
lesson.
supposed to?
We were supposed to take a statement with our answer.
A statement or just say that we did?
Statement. Do you think he's gonna be able to verbally keep track of all this?
What?
Saying
Mason,
we
did you
Googled it or
Google
not?
it?
No, no. I wrote that I Googled it. I just did not write a statement.
It was like 9:30 or
Carson walked on
something.
this.
That's good. I'm pretty sure Carson Googled it though.
No,
I
he
saw
didn't.
his-
He said he did it.
He said he didn't.
I saw his proof basically verbatim, and it had like these very similar steps as to one I saw on the internet.
Just because it has similar stuff doesn't
It's
mean
exactly the same. Hopefully it's just a coincidence.
Or maybe
There's
that's
only a
because
few
somebody
ways you
said-
could do it.
Yeah, but it's exactly the way it was on.
But he's not gonna like pull up 10 different Google things.
Maybe he knows that I'm not talking about though, because he's one of the first results.
But like, I mean, I didn't use Google. I just kind of plugged it in and did it algebraically like we were doing in class. But if that happens to line up with a website, I can't help that.
Yeah.
You know, I didn't
That's
use the
right.
internet. So.
Yeah, there were just little quirks in it that were exactly on the website. But you know, that's
But
okay.
I made it longer, like the stuff where you could like, you had to multiply to get rid of the denominator and the numerator. I showed my steps exactly for that, just so there's no question. You know?
Why?
Get rid of these crappy glasses that hurt my eyes. Oh, not today, Thursday. These hurt my eyes. I mean, they'll help me, they'll hurt my eyes.
So does that mean you
Really
can wear
badly.
glasses now? If you get
Hopefully
better
not.
ones? Hopefully not, but I'm blind.
Hopefully contacts,
Oh,
if I can go through with that.
they're expensive.
Yeah,
I hate glasses.
you ever fallen asleep with contacts?
Ew.
You wake up like all crusty eyed.
Or you watch someone take them out.
I mean, I knew they had lenses on their retina, so.
Yeah, these hurt my eyes. So no matter what, they new glass. These really hurt
Yeah,
my
I
eyes.
had to get used to these. But when I went to I just
Oh, that's pretty good.
so I never look at glasses, so
I mean, I'm surprised by the difference then, but even back then, it hurt me way too much, and still it hurt. A few years ago. Quite a few years ago. Was it 7th grade? 8th grade? 6th grade?
These are for my
Oh yeah, I want to say these are
Around your machine just means. Oh,
No, these are actually kind of recent.
Are they like the same?
Well, they're not the exact same.
oh, that's plus, I mean, just, yeah, that's cool. So,
Hey, I'm pushing.
It's the same as a strap.
What? Yeah.
How is Will Maker so powerful? That's the next theory I'm gonna make. And I'm collabing with Andreas on it.
Are there any good stores in Chapel Hill?
Yeah. CVS.
Hey, State has one too.
Dude, I have a CVS now.
hey, let's go and get started now. If you have the, decided to do that first rule, like that off.
We're ahead of the game.
Do that?
We're ahead of the game. We already turned it in.
Or turn it in, fantastic.
I'm surprised he was.
Y'all are ahead.
Yeah, same.
Okay, so, let's start with, let's go over real quickly question 1, and then we'll see what questions you have on the rest of the homework that you're supposed to practice on and go from that. So first, let's do question 1, get that knocked out real quick. The basic concepts. Computer start us off on 1A. Okay. Okay. Treat that as the derivative with respect to x of 5.
Equal here. I said that was true. And is that the constant?
That's the constant rule, exactly like that. Okay. 1B. That's the Mason.
True or false? D over dr times ks plus r equals k.
Wait,
And
wait.
this is false.
Time out. It's
Sorry,
not sorry.
the derivative.
Wait, how are you supposed to read
Okay.
it?
Yeah.
Well, you can say d over dr, that's fine. Just don't say times, say of.
Oh,
d over
sorry.
dr of, or derivative with respect to r of, but it's not times, it's of. Okay, go, keep going.
Derivative of ks plus r equals k. And this is false due to theorem 2.8 part C. It should be d over ds rather than d over dr in the formula.
Correct. To get a K response, you're absolutely right. What should it be with the derivative as written? What should the answer be with the derivative as written?
With the derivative as written, it should k. Should be k. No.
What are you saying for?
Oh, wait.
What is he saying for this
Derivative.
one?
So it's d over d. If it was d over d s of ks plus r, then the derivative would be k as written. So if the with respect to, it's the derivative with respect to r is how you read that. So if the with respect to had been s, then the answer would be k. I agree by the linear, not linear, but the linear theorem. My question is, if the derivative with respect to r, what should the derivative answer be to be true?
Is it 1?
Be 1, that's right. How did you get a 1 right now?
If I'm being honest, I would say intuition, but
Hey, you know what? There's always a place to go into Vegas and win a lot of money on that kind of thing.
yeah.
Good intuition. So if the variable in this one is r, then that means k and s both are constants.
Oh gosh.
So the derivative of k times s is 0, because it's a constant. And then the derivative with respect to r of r is like taking the derivative of x to the 1. It's r to the 1. So you get 1
Gotcha.
r to the 0, which is 1. That makes sense now?
Yeah.
Okay, so C, we're at C now. Yes. Yes, it's true because of the linear theorem that we're doing with respect to s. So s is our variable, and k and r are constants. That's right. D. 1D.
Indeed.
Please, if you want to take that one for us, please.
You say use good? Who did you say, Mr. Gaddis?
Please.
Okay. True or false, the derivative with respect to x of 3x plus 1 to the power of k. And it is true because that's the, what is it again? We just did it yesterday.
Well, it's partially true. It's not absolutely true. You can. This is similar to the problem we did yesterday. We had a product rule. We thought that the derivative of a product was product of two derivatives, and it turns out it's not. The product rule is more complicated. Well, the same thing here. If this had simply been x raised to the power of k, then that would be true. But with a 3x plus 1 in there, it gets more complicated. As an example, so quickly, someone go here to the middle board. So you have 3k plus, sorry, 3x plus 1 raised to the k, and we're taking the derivative with respect to x. So let's try k equals 2. So let k equals 2 and see what we get. Book says, is this equal to, question mark, we take to 2 times 3x plus 1 to the 1.
Which is just 2 times 6.
What if I actually distribute it out? So 3x plus 1 to the square power, and then I'm going to take the derivative of it. This is a 2 here. So then if I distribute that out to see what I get, then I'm getting the derivative of 9x squared plus 6x plus 1. And if you apply the sum rule on all of these, you won't get that, I don't believe. So we can pull off the 9, bring the 2 down, so you get 18x to the 1. This just becomes a 6. That's a 0. So 18x plus 6, if I distribute that out, 2 times 3x plus 1 is 6x plus 2. These two are not the same. So it could be true once in a while, but in general it's not true because here's an example where it's not true. Okay. How about one, E? Volunteer for E? Okay, Justin?
True or false? D with respect to x. Oh, we go E, right?
Right, E.
Okay. True or false? D with respect to x is 1 over x cubed 3x squared. And that's false because you have to do the
Yeah, you can either do the push rule or you can do another thing. I agree it's false. I want to come back to that one in just a minute. Well, I guess while we're talking about it, let's talk about it. Okay, so Justin said it's false. I agree, and he says because you need to do the push rule, and I agree that's one way of doing it. Another way, let's go over this for you. So let's see, what does it say? The derivative with respect to x of 1 over x cubed. What it says? Okay, so again, you can read this as d by dx of this expression, or you can read it as derivative with respect to x of this expression. Anyways, I can do this with a quotient rule as Justin suggested. Let's try that real quick. So if I use the quotient rule, I do the derivative of the top times the bottom without derivative minus the top times the derivative of the bottom over the bottom squared. That's plain and simple, called the quotient rule. We didn't prove it. I asked you to try to prove that on extra credit, so I'm hoping you did, or at least you can say, amen, I believe it's true. It's not that hard to prove. So the derivative of 1 is 0. So 0 times x cubed minus 1 times, this is going to be 3x squared over, this is x to the 6th. I get negative 3x squared over x to the 6th, which is negative 3 over x to the 4th. So this is not equal to whatever the book had. What they have? 1 over 3x squared. So this answer and that and what the book has are not the same. Now, I suggested that, yes, I could do this with the quotient rule, but what I also want to say is I could do this more simply, I believe. Or, what if I rewrote this as
Oh, crap.
1 over x cubed, the same thing as x to the negative 3? And now I'm almost done. So I can get the same answer, but more quickly. So honestly, folks, anytime I can avoid the quotient rule, I'm going to avoid it. The quotient rule is kind of messy. Sometimes you can't avoid it, you got to use it, so you need to know it. But in a situation like this, it's easier if I rewrite that expression, not as a quotient, but as just a regular expression, and then I can apply my power rule, which gives me negative 3x to the negative 4. So this is just this plain old simple power. And that is...
That's awesome.
So, again, you got to be able to do the quotient rule. There'll be times when you can't avoid it. But when you can avoid it, take the shortcut if you can. Okay? Okay, back to regular schedule programming, 1F. All here. All here somewhere. Razor, good, thank you. Yes, Ray.
F, true or false, if f and g are differentiable functions, then f of x times g of x, the derivative of that, is equal to the derivative of gx times f of x plus derivative f of x times g of x. And I said that's true because that's just stating the product rule.
Yes, that's just, they have reordered a couple things, but are you allowed to change the order of multiplication? Yes, so, and or addition, so that, yes, that's the restatement of the product, like that. How about 1G? Volunteer? Sam? Oh, wait, okay. Josh?
Okay, true or false, if g and h are differentiable functions, then the derivative of g of x over h of x is equal to h of x times the derivative of g of x minus g of x times the derivative of h of x over h of x squared. And I got that was true due to the quotient rule.
Absolutely, I agree. How about 1H?
What kind of a question is this one?
True or false? Proving the sum rule for differentiation. We did that yesterday. We proved the sum rule for differentiation. What did we have to do with the sum rule for differentiation? A lot of algebra. Started with the definition of derivative, which put us into an algebra format. We did a bunch of algebra, and eventually we had to apply the limit rule that says I can go across the sum inside of a limit. And that allowed me to split my limits out into two pieces and then do the derivative of each piece. Get the answer as the derivative. So I'm going to say that 1H is true, that's what it takes to prove that. Okay? Any questions on problem 1? All right, what other questions do you have on homework that you ran across? Brittany, yes.
Number 27.
Okay. 57, 59, let me write down a couple numbers here. So, 57, 59, any other one, four maybe, Razo?
67.
7, okay. Let's see how that, if we get through these, see how we'll feel after that. Okay, so back to, I'm going to go back to that. Go back to that one. 27. Oh my gosh. We're supposed to, on 27, we're supposed to find f prime of -1. Given that, f of x equals.
Yeah, I don't think that's a 27.
It's
I'm
28.
just saying.
Oh, it's not f prime of -1, it's f prime of 0. I'm reading the wrong problem, number 28. 27, back to 27. 3 times h of x over
GX.
x plus j of x. Oh my gosh.
What's going on?
So I need to, in order to find f prime of 0, I'm going to find the f prime function. Agreed?
Yeah.
What do you observe? The f function is defined as a quotient. So to find f prime, I've got to use the quotient rule.
Yeah.
So f prime of x is equal to, by the quotient rule, derivative of the numerator times the denominator without a minus numerator. That's the page next there. Got my 3. Minus the numerator times the derivative of the denominator all over denominator squared. This was the quotient. All I did was just laid out my quotient rule by the rule. Derivative of the top times the bottom without derivative minus top times the derivative of the bottom, all divided by the denominator squared. So now I just have to go in and find all these little pieces of derivatives. Oh, derivative of 3h of x. What does that mean? It's right here. Focus on that. Derivative of 3 times h of x. By the multiple rule, it is 3 times h prime of x. So once again, I simply did multiple rule. Now over here, I've got the derivative of g plus j, so that's just going to be the sum rule. And so that's going to be g prime of x plus j prime. And I've got of x plus j of x squared. I'm not going to try to simplify any further because I've done my derivatives. All I have to do now is, it said, to find the value at f prime of 0. So I just have to plug a 0 into this to get my answer. So f prime of 0 looks like it's going to be, if I use this information right here, 3 times h prime of 0, 3 times h prime of 0, times g of 0 plus j of 0. Make it small because I'm out of room, but I'm just following this formula I've created and plugging in. Minus 3 times h of 0 times g prime of 0 plus j prime of 0 over of 0 plus j of 0 squared. Now I can use my table. Whatever h prime of 0 is 3. Y'all with us now? It's just plugging in now. So 3 times 3. 0 and j of 0. 0 is 2 and j of 0 is 0. 2 plus 0. 3 times h of 0 is 8. G prime and j prime of 0. Negative 2 and negative 2. G of 0 and j of 0. 2 and 0. So now it's a little bit of arithmetic to get the final answer. You follow all this? The thinking process there? The application of the properties and rules? What follows here? I'm not done. What's the final answer? Someone give me a. I wouldn't do this. Let's see. 9 times 2 is 18. We got 9 times 4 is 36, and 18 is 4654 divided by 4. 44 divided by 4 is
27 divided by 2. That's
7 over 2.
a simplified version.
Thank you. 27 over 2.
Thanks, Sammy.
So what does 27 over 2 represent? The number we just calculated. What does that mean? What does it represent? Yes, what does that tell me?
The tangent line.
On the function f, that's correct. So on the function f, the tangent line at point x equals 0 has a slope of 27 over 2. That's what that tells me.
That's nice.
Okay, can you follow that? 27, everyone?
I'm not getting that at 27 over 2.
Where did I get 27 over 2? Maybe I did my arithmetic wrong. So this 3 times 3 is 9, times 2 more is 18, right?
Right.
And then negative 2 and negative 2 is negative 4. Negative 4 times 9 is negative 36, but we're going to subtract negative 36. It's really adding 36. So 36 and 18 is 54 divided by 4. Okay. That's 27. Now 51. We'll move over here now. 51. Directions for 51. Use the differentiation rules. Find the derivatives. Note, it may be necessary to do some algebra before differentiating. And in some cases, they don't say this, but in some cases, instead of required, it may be advantageous. So sometimes it's required to do some algebra before you do derivatives, other times it's advantageous. And I think 51 is going to be advantageous. Okay, so at first inspection, I see that f of x is a quotient. So I could, in fact, apply the quotient rule. It absolutely does apply here. But if we do a little bit of simplification, a la over here on the earlier problem, then it will be easier to do this problem. So before I even start thinking derivatives, I'm thinking ahead that, hey, I got to do a derivative. How can I make this simpler on my life? I'm going to recognize that I've got x's in the numerator and denominator as factors, and therefore I can apply the properties of exponents to simplify this. So this is x squared over x to the 2/5, my property of exponents. And then also by property of exponents, 2 is the same as 10/5, and if you subtract 2/5, you get x to the 8/5. So now that's going to be a real easy derivative to achieve. So f prime of x is the derivative of x to the 8/5, which by the simple power rule is 8/5 x to the 3/5 by the power.
I love it. I did the quotient rule and I wanted to die.
Quotient rule, you know, I don't know.
I don't know what the book has as answer. They may have converted it back to radicals, but I'm good with right there. I'm done.
Yeah, I'm pleased.
They didn't convert it back to radicals.
Okay, questions on that one? Okay, you can absolutely do the quotient rule, and it's not going to be wrong. It's just going to be longer. So, again, you need to know the quotient. You will have to use it sometime. Here's a time that you don't have to. Number 59. Okay, 59, you're going to have to do the quotient rule. There's no way around this one.
Oh, man. I thought I could get away. 59. Why would they make a question like this?
F of x equals 2x minus 3 over 5x plus 4. So why is this one different than the one right beside it? Look at the function. What's different about these two functions? That on the first case, I can simplify and make my life easy for doing the derivative, but on the second case, what's different? And just in looking at it, you'll look at it and say, I can do this or I can't do this. What's different? Why not? These are two factors, right? So I can simplify by exponent rule. These are not. These are terms. Now, if it was factorable in some fashion, you could do something with it, then that's one thing. But it's not factorable. So I'm kind of stuck with, I got to do the quotient rule. Okay, so let's do the quotient rule. F of x equals, quotient rule is going to be the derivative of the tops, derivative of the numerator, times denominator without derivative, minus numerator times derivative of denominator, all divided by denominator squared. This, I'm just, all I did there was apply the quotient rule to achieve that. Okay, so within the quotient rule, I still have derivatives to do. I still see a derivative with respect to x. That means I still have more work to do. I see another derivative with respect to x. It means I have more work to do. So to find those, I focus on just doing that one little piece, this derivative of that stuff. And that's going to involve what rules can I do there? I can use just the plain old linear rule in the book if I want. Do we see that this is just linear? And it has one just, you know, or you can do it. And you can do it as a sum rule, absolutely. Or you can just say, well, that's linear. That's just plain old linear. So the answer has got to be 2. Okay, so this time we'll use the linear rule. So that's just a 2. Again, the rule that allows me to do that is the linear rule.
I don't remember writing that.
And this one over here is linear as well. So that's going to be a 5. And then just pause for a moment, make a cautionary note. It's really easy for students, in my over 20 years experience, to lose this denominator. They get so focused on doing these derivatives up here, and these were simple derivatives, but it can get more complicated quickly, as you'll see. But if that denominator gets lost, the answer is not correct. So keep up with your denominator all the way down through the process. It's just an easy oversight. I'm just kind of warning you, don't lose things along the way. Just because there's a lot of heavy work up here, don't lose the little thing that's also important. This one I'll probably want to simplify a little bit just because I can easily do that. So let's see, if we distribute, we got a 10x there and a negative 10x there, so that goes away. And then an 8 and a plus 15 is a 23.
That's it.
Did I do something wrong?
Oh, never mind.
I don't know. I think I did it right, but I'm please, if it's wrong, let's correct it before we go further. So 10x and negative 10x, and then 8 and negative of negative 15 should make 23.
You mean positive 20?
Questions on this one now? Oh, I would be. Good question. Question on the floor is, do I leave it like this, or do I expand out that denominator? And the answer is either one, but I would recommend leaving it like this because, here's why. You want to simplify your answer as much as possible. To simplify in pre-calculus, you needed to have factors on the denominator, so try to cancel the factors. If you distribute that out, you don't have factors. So it's best, in my opinion, to, even though they're equivalent, to leave it factored. So this is the answer I would leave as the answer. If you expand it on the test, I'll give you credit as long as your expansion work is correct. But first, make sure that nothing else will cancel before you expand. You understand? I want to simplify as much as possible. Okay. Where are we? Number 67. Yeah. Okay, absolute value 1 minus 2x.
Absolute value got me geeked.
Find the derivative. Well, before I can find the derivative, I have to have a function I can deal with. And sadly, although absolute value is a fun function because, you know, hey, the answer is always positive, I can understand that in 6th grade. But I need a real function I can deal with. So what's the definition of this function based on the definition of absolute value? I want a function rule that I can work with.
Is it going to be a piecewise thingy? Is that what you're asking for?
Yeah, so I want the piecewise definition of absolute value function.
You want 1 minus 2x for x is greater than or equal to 0?
No, we'll come back to that.
Okay. Dang it.
So, which case do we do? Where we do the positive case if the input is positive, and we do the negative of it if the input happens to be negative. So that you make the output positive. But what's going to be the deciding point where we change from positive to negative as your input here? It's not at 0, but at half.
I'm by.
So
Okay.
okay, but which way is which? Do we want x to be, in the positive case, do we want x to be bigger than 1/2 or less than 1/2?
Well,
1 minus 2x to be greater than 0. Algebra, folks. Negative 2x is greater than negative 1, so therefore x must be less than 1/2, right? Less than. So if this is less than, and we typically put the equal sign on the positive one, and then this must be greater than. Well, what we're going to do is I'm going to put the x equals 0 as its own thing here.
Zero.
Oh,
I'm geeked
I'm
right now.
confused too.
I'm geeked at 7 in the morning.
So yes, I just made an argument why the answer on the end was not 0, and then I wrote 0 after making my argument. So yeah, that was. I didn't follow through on all the little pieces, did I? I lost my denominator in there somewhere. Okay. So I'm going to separate it into 3 pieces. Instead of combining the equality with the one part like we normally do, I'm going to separate down equality because that's going to become important to us when we do the derivative. Okay, so first of all, is the function continuous? Is f of x continuous at x equals 1/2? That's the first question. So we need to know that.
It is continuous.
So the question is it continuous? And I hear the answer is yes, it is. How do you show that? Raisley, you said it is continuous. I think I agree with you. But how do you know? How do you show that?
If I remember correctly, you guys show that as it approaches x equals 1/2 from both sides, it's approaching the same value.
Yes. So limit x approaches 1/2 from the left of f of x. So if I'm smaller than 1/2, I'm using the top rule up there. So what does that go to? That goes to 0, doesn't it?
Mm-hmm.
Look for 1/2 up there. And the limit x goes to 1/2 from the right of f of x also goes to 0, and f of 1/2 is equal to 0. Since all three of those things are the same, then we say, yes, it is continuous. Remember this now from the last chapter? Okay, so that's continuous at 1/2. That means what in terms of derivatives? Before we go further and do the derivative, what does that mean for us? It may be differentiable. Remember the rule said, the theorem said, if it's differentiable, then it's continuous. The differentiability can guarantee continuous. But what that meant is, if you weren't continuous, then you cannot be differentiable. I'm saying that potentially this is differentiable at the point 1/2. Otherwise, who knows? And now let's actually find the derivative. We'll do it in pieces. So we're going to split it up with the same split up. So in the first rule up here, when x is less than 1/2, if we apply the derivative rule, what derivative rule do we need to apply to find the derivative of this piece, the first piece? I'm just focusing my attention on the first piece now. So I'll even use color shades. So we're focusing our attention just on this.
Can we do the linear?
That's going to be linear. And what's the slope of that linear function?
-2.
-2. Derivative is -2.
I love it.
Good. Now let's focus our attention on this part. That's a linear function also. And what's the slope of that linear function? Positive.
2.
Okay. So now, in order to determine what the result is at 1/2, we have to, like over here, we have to do the derivative from the left side derivative and right side derivative. You all remember doing this?
Yeah.
So I got to look at what is the derivative on the left side of 1/2, and what is the derivative on the right side of 1/2. On the left side of 1/2, the derivative is, if I'm approaching 1/2 from the left, what derivative value do I get?
-2.
-2. If I approach 1/2 from the right-hand side, what derivative value do I get? +2. Since these two are not equal, then that means what? Prime of 1/2 does not exist. So what we'll put up here is does not exist. I don't know. Okay. Let's do here. I'm going to take a couple minutes to talk about the next group of exercises in case you had trouble with those. 73 through 77. Did y'all try any of those?
I'll just. I don't get it. Mr. Gaddis,
Yes, right.
can I ask a question? The last and that question we just finished, I'm sorry for asking this once you were switching gears, but I need clarification on something.
Okay.
When you were talking about the left and right derivative,
Yes.
why did you get the difference with like the left side getting -2 and the right side getting +2?
Well, when I was left of 1/2, I was using x values that are smaller than 1/2 So that means I'm using this derivative rule.
Okay. So it's just
Derivative rule
approaching.
gives me an output of -2 for any x. That makes sense now?
So it's just approaching the other pieces.
Yes. If this had been a function that had x in it rather than a constant function, then I still would use that function as the left side derivative, and I would use this function as the right side derivative, and I would see what those would approach as my x value gets close to 1/2. So I mean, I might have something like -2x plus 9, and I might have 2x minus 3 here. Okay, well, as x gets close to 1/2, what do those derivative values approach? You understand? It's not always going to be a constant number. I just use the left side and right side of the value 1/2 to see what my derivative values are getting close to. Does that make sense?
Mm-hmm. Thank you.
Happen to be constant this time. It's not always going to be constant. Okay. On the last group of exercises, they talk about something that we haven't mentioned before. Let's define a function given the derivative function. So we need to talk about that for a minute. So let's make up a problem. Given f prime of x equals, make it simple to start with 2x plus 1. And we'll start there. Let's start with that. We'll add 2 into that. Find a function of x we'll find this function f. We got to find. Let's call it f. Find function f of x. So this is going to be called this new function. What we're doing now, instead of differentiating, we're doing something called, but it's very heuristic at this stage. We haven't formalized it yet, but the book is just introducing it. We're doing what's called anti-derivative.
Oh, that's awesome. That sounds so cool.
Well, ought to make sense. If differentiation is doing one thing, then what do you think anti-differentiation means?
The opposite.
The opposite, right? So instead of starting with the function and finding the derivative by the rules we've learned, they're suggesting kind of guess and check. Think about it and see if you can come up with a function f of x whose derivative is that.
Yeah.
So can you guess and check? So we're just going to guess.
Whoops.
In order to get a 2x as a derivative, right here, to get a 2x as a derivative, that is the derivative. What did you need to be at in order to get a derivative that is 2x?
X squared.
X squared.
We'll use some color for that as well. Make sure everyone's with me. So 2x came from, if I had an x squared, then the derivative of x squared gives me a 2x. And then what would I need if I'm going to take the derivative of a function and I'm going to get the number 1? What did I need to have started with to get a derivative that is 1?
X.
X. Right. Y'all follow that? Now check it. Make sure. Okay, so we all see that if I use my sum and power rules, I get back to where I started. We all agree with this? Fantastic. I have another question for you though. What if, just because I feel like being honoring,
Honoring.
you ever heard of honoring?
Ornery?
My grandmother called me all the time. I was
Of the old man.
honoring as a kid, not a grumpy old man, as a kid. Honoring. What if I decided that my function, I don't like this one. I wanted to put a plus 3 right there. I just felt like putting a plus 3.
It won't do anything. I'll tell you that much.
Because if I put a derivative with a plus 3 right there, do I not still get back to the same thing? Because what's the derivative of that 3?
Nothing.
0. It's 0, that's right. So, what it means is that in general, a function that's the antiderivative is really represented by a family of parallel functions. So, if you recall, remember doing the slope field business? I remember this. Let's look at slope field for a minute, and then we'll come back to that. Slope field just reminds you what we've done before to tie it back. So if I have function f prime of x equals 2x plus 1. That is a linear function that goes through 1 and has a slope of 2. So there's my derivative function. Now, if I was going to try to sketch a graph of it, we've done this before already in this class. If I was going to try to sketch a graph of f of x, you remember doing this? We made a slope field. We said, well, right here, the slope is 0. So I'm going to put a bunch of little tangent lines that are, so that point tells me the tangent line is 0.
Oh, crap.
That tells me the tangent line is 1. So we're going to put a tangent line of 1. And there it tells me the tangent line is even steeper. Back here, my tangent line is -1. Back here, my tangent line is even more negative. So I got what was called a slope field. And then I could go in and I could pick any starting point and draw a graph of it. We did this on the previous test. Remember doing this? So I could have started right here and made sure my tangent lines just stayed tangent to my curve. I got that. But what if I, instead of starting right there, what if I decided to start right here?
You could.
I have two function graphs that are both equivalent, except that one's just a transformation of the other one vertically by a shift of some amount of distance. It's a vertical shift. For pre-calculus, a vertical shift involves adding on a constant at the end. So what we do is go in here and we say the antiderivative, instead of using 3, say that it is any undeclared constant C.
Wait, could you not do 3 then? Or are you
It could
just
be
making
3, it could be 3, it could be 17, it could be -9.
Okay.
It depends on how you shift this function up and down the scale. Okay? But now here's the next part of the problem. What if, instead of just any, this is all, we call this a family. This is called a family. This is called a family.
That's what. Oh. I thought you were just saying.
Antiderivative.
Oh, that's cute.
But now let's suppose in a given situation that you're not as interested in the whole family. I mean, all of them, Aunt Harriet, Uncle Henry, cousin Waylon, whatever, all these family members are in there, but maybe there's only one that you're really interested in. That really sparks your interest, and you need to get to know better. So let's suppose that the one we're interested in goes to the point, let's say it's this one right here. It goes through this point, that point is going to be at 1, -4. So the cousin who goes through point 1, -4 is the one I'm interested in. How am I going to figure that out? Well, over here, I have a function, and the C tells me it can be any value on the end. It just shifts the whole picture up and down. But how am I going to figure out what that C value is so that I shift it the right amount to go through that point over there, 1, -4? Well, here's how. This is the second problem. This is problem 1, problem 2. Find
Locate cousin.
One cousin, antiderivative, that passes through point 1, -4. So how am I going to find that one person?
That was good.
I have a function, f of x right here. We all agree this is a function. It happens to have an undeclared constant in it right there. Okay. But I now know a point that that function has to go through.
Oh.
That statement now tells me that f of 1 has to be -4, or else I've hit the wrong cousin. You don't want to hit the wrong cousin because they might hit back, you know. So how do I deal with this?
West Virginia. Not me.
1 squared plus 1 plus c has to equal -4.
Oh, this
That's
is
what
great.
these statements say. Agree?
Yeah.
F of 1 equals -4. So I'm using my function, plugging in a 1 and setting it equal to -4. Now you can easily solve. C is equal to
2.
6.
What? Am I dumb?
What did you get?
Oh, I can't add. I'm dumb. I'm sorry.
What did you get?
That's okay. I can't either. I teach math. I can't. So what does that mean? The cousin I'm looking for, therefore my final answer here is f of x equals x squared plus x minus 6. That's the one cousin I was interested in.
John rolled on. Sing money.
Now,
My cousin Vinny, you know. Isn't my cousin?
that can be used.
No. My brother Vinny?
10 minutes. Okay, we can knock this out. Okay, with that concept, we can now discuss the general free-falling body function that we use on the Galileo problem. Remember that one, the -16t squared plus 20t plus 100 on the last test?
Yes.
We can discuss that now, a little more understanding from what we just did. Okay, so recall I want to show how this comes about. Recall on test, we had the position function for the falling bocce ball. He threw the bocce ball up and then it came back down. It was this -16t squared plus 20t plus 100. And the 100 was the starting height, 20 was the starting speed that I threw it at, and then that has to do with gravity, but 16. Well, how do I show that? How do I understand that from what we just went through? Okay, so going all the way back again to Galileo, he determined that the rate of acceleration of a falling body was constant. That was what he determined. And so that means the function that's called the acceleration function is constant. In fact, it turns out to be a constant, -32 feet per second squared.
I don't know how he did that.
This is how it really developed. They didn't start with the position function and then take derivatives and get the other. That's easy to do. But they really started with a known constant acceleration and figured out the antiderivative by a little guess and check here. So acceleration is the derivative of which function?
Velocity. Velocity.
So that means velocity has got to be the antiderivative of acceleration.
It's the antiderivative.
What I'm asking you now is, what needed to be here so that the derivative is that? Negative 32t plus, call it constant, and I'll put a subscript v for constant for the velocity. We'll have one in a minute with position. But I don't want to just leave it the whole family out there. That's too many people to deal with. I rather just know one person. So I need to figure out what that. What information did you know in the original problem on the test? Do you remember what it said in the problem? He threw it up at 20 feet per second.
Good for him.
Threw,
Sam.
he hurled, he threw up. I mean, it's like
20 feet per second. Okay, here we go.
20 feet per second.
Through it.
You take on projectile. Okay, no, let's stop there. So that means that we can write this as the velocity at time 0 was 20. Would you agree with that's what that statement says? Right at the initial, when he releases, right at time 0, that ball is going 20 feet per second.
Oh, that's cute.
Can we use that now to figure out what BC is?
Yeah.
Yes.
We can find my.
So if we use this information, we've got negative 32 times 0 plus CB is equal to 20. So that's just using that information. So that means CB has got to be 20. My velocity is negative 32t plus 20. And that's in feet per second. Okay, let's do one more.
Yeah, it's my Richard.
Suppose that I know this velocity function now. Before you guys start thinking a little harder, I want to know a position function. I know I've already given it to you, but I want you to think about it without knowing that up there. Can you look at this and say, I want to find a function whose derivative is that? So, to get a t in my derivative, I've got to have a t squared here, right? Y'all agree with that? Agree? But when I take the derivative of t squared, what happens with that 2? It goes down and multiplies. If you're going to multiply times 2 times something to get to 32 negative, what does the something in front need to be?
Negative 16.
Y'all follow that thinking? Yeah, I know the answer's written on the board, but y'all follow that thinking?
Yeah.
One more time. When you take the derivative of t squared, you get 2 times t. But if there was another coefficient multiplier in there, you just multiply that 2 times that coefficient. But 2 times some coefficient has to give me negative 32. That coefficient needed to have been negative 16, which is what we have written over there.
I love it.
And then we've got plus. Now, I want to get a 20 as my derivative. A 20 as my derivative. What needs to be up here so I get a 20 as a derivative?
It's 20t. I love it. It makes sense.
And then plus, what we don't know yet is the constant at the end because we did an antiderivative. So we'll call it the constant of position.
Is that S right there?
That's an S, yeah, for position.
Okay.
And then we know, what did we know? What was given in the problem? He's standing on tower of Pisa, so it's 100 feet up in the air. So on tower, so that means position at time 0 is 100. So now I can use that information one more time. -16 times 0 squared plus 20 times 0 plus the constant position is 100. The constant is 100 because the information I knew was at time 0. That means my position function is as stated over there, -16t squared plus 20t plus 100. That's in feet. Now, let me emphasize that if your information provided is not at time 0, you understand, you can still figure out what that constant is, but like over here, I didn't give you time 0, I gave you like time 1. It doesn't have to be at time 0, but you still can figure out what the constant is. Are we clear on that? Mm-hmm. Righty. So, in general, for any planetary type of orb, the position function of a falling body is -1/2 times g times t squared plus b0t plus this.
Can we zoom in?
That's basically what we just went through. So S subscript 0 stands for the starting position at time 0. B subscript 0 stands for the starting velocity. So in this case, he threw it up at 20. What if he threw it down at 20? That would be -20 here, not +20. Are we with this? Mm-hmm. And then -1/2 times the gravity. If the gravity on Earth is 32, then we put a 32 in there, feet per second squared. Gravity on Earth is 9.8 meters. You could use meters instead of feet. But on the moon, for example, the gravitational acceleration, one second, Razor, gravitational acceleration is not the same as it is on the Earth. So it wouldn't be a 32 in there. It's much smaller because the moon is much smaller, so less gravity. Saturn or Jupiter, much bigger, so much bigger G value. But the formula is still the same. It just depends on the G. Yes, Razor, your question, please.
Where does terminal velocity come into play in this?
What is terminal velocity?
Where does it come into play in the calculation of that?
Well, it doesn't in this one, because, good question. In this one, we are assuming negligible wind or air resistance due to being close to the Earth. 100 feet is close to the Earth. And dropping a aerodynamic, like a ball or something. Terminal velocity comes into account when you have something that's less aerodynamic, like, say, a human falling out of an airplane with their legs and arms splayed out, and from a greater distance. At that point, the wind resistance eventually builds up to a point where your body, even though there's still gravity pulling on it, trying to make you go faster, the wind is so strong in your face that it slows your body down, and you stabilize at a constant velocity. And that's called the terminal velocity. So for a human, I think it's around 150 miles per hour, something like that, which is, at that velocity, when you hit the ground, it will be terminal.
Got it.
It's called terminal velocity because normally, if you don't have impedance by the wind like that, the velocity just continues to grow. The ball just keeps going faster and faster until it hits the ground. But again, at greater distance, further from the Earth, and with a non-aerodynamic object, wind resistance does come into play. Now you got to start accounting for that. That's a whole other engineering realm that we'll not get to in here. So Good question. But we'll go simple and keep it low, close to the ground, and aerodynamic objects that don't get affected by the wind. Good question. Yes, please.
Is this where the equation from physics came from, or did this come from physics?
I couldn't hear you. Please, one more time.
Did this equation come first from calculus or physics?
Well, calculus didn't exist back then, so.
Well, a little. I mean, honestly, at the time, physics and calculus were kind of one and the same. You had Newton, Galileo, and others studying the physical world, the planets orbiting and stuff, and they created calculus to develop the formulas to model the physical world. So I would say the answer is yes. It kind of coincided. The physics and the math kind of coalesced at the same time and came up with these formulas. Ask a physicist, he'd probably say the other way around. The mathematician only would say the math came first. So anyways. All right, well, finish up on your homework. Go ahead and read section 2.4. 2.4. And we'll do that tomorrow. Tomorrow.
Do we have any homework for 2.4?
No, I think we're just reading it.
Assuming we do number 1.
We'll just do number 1 for kicks. Actually, wait, I don't even. Yo, velocity got me. Oh yeah, Sammy. I need to see that question. Where are you going after this?
Does anybody have any questions on their test?
Yeah,
that they
it's
want answered?
everything.
Not really.
No. You're not looking at the tangent lines. You're looking at like f prime of x. You have this picture of f prime of x. Whatever it might be.
She's
You're trying to say,
continuous.
well, okay.
I only use abbreviations, so I say.
I got that one. That right there.
Sammy.
That
Oh, I thought you were leaving.
that
Yeah.
has to be.
I can just tell you with answers since it's actually really simple.
Can you type it on my phone?
I don't want to type a word from her. Someone else uses the answer from her.
So she knows what?
Yeah.
I don't think I can read it.
So
Basically, if you look at the graph, the
And so,
speed
like,
of
you're
it
going
when you
through and
first do
saying,
it
okay,
is the same as when it
slope is
reaches up here.
Yeah, that's okay.
So when it falls back down to that 100 feet, it's 20 miles.
If you look at the graph, the speed at which he started throwing it is the same as when it landed?
As when it got back to that same height.
Is when it got back to, okay. If you look at the graph, the speed at which he started throwing it is the same as it got back to where it started.
Just in general, what do you did in class and that?
And therefore, like when they shoot the guns and stuff on New Year's, that same speed that the bullet leaves the gun, when it comes back to the ground where you're standing, it's gonna be at that same
And
speed.
so
The same speed the bullet leaves the
here,
gun,
the
it falls
slope
back at the same
is
speed,
gonna be negative because it's below x,
which is dangerous.
right? And so your slope.
I mean, it's pretty basic when you.
Yeah, I just didn't know what he wanted me to pull from it. Do you even want to ask thing or anything?
Your
Or?
slope is gonna be positive, and then right there,
I'm just gonna listen anyway.
right, you're gonna have that term where it starts increasing more.
Oh, is this the same
Is
thing?
it increasing on?
And
Oh,
it's
so is
zero
it just-
here, because it's zero there,
Yeah.
right? And so that's gonna be, you got that part.
Is it?
Well, all of this is gonna have a positive slope because it's greater than zero.
Oh yeah, I'm gonna ask for one question,
That's
Mason.
gonna have a negative.
Did you get the one where you had to
So it's gonna
define
be
what a
going
limit is?
down, this is gonna be going up, and this is gonna be going up steeper.
You should look at it, come here.
I don't have my test with me. It's
I mean, that's what I would think.
on my
So the
desk.
slope is positive here, and it's increasing
Cause I
more
found this
rapidly.
down.
So your slope field would kind of go zero, and then it kind of goes that way, and then it kind of goes that way again, and then it starts going.
Okay.
Does that make sense?
A little bit, yeah. And then this one just needs to be.
Okay, so he circled this, or was that you that circled it?
I don't know. Let me look at my original.
Yeah, I mean, that one, I don't think it's hard to go.
line, he circled secant line.
From
Does it have to be
the f of
tangent
x to the
line?
derivative. It's harder to go from the derivative back to f of x.
The function itself,
And you
which
only
part
use
of the
slope
function?
fields when you're going backwards.
Oh yeah. I mean, it's just it's
The derivative of
I got 6. That's what I got, but I didn't get this part, I don't know where this one.
So on this, what I'm thinking is the acceleration has to be less than 0
Oh, dang it.
for the whole graph.
I don't know
Right, so
how you
it
guys do
always has to be decreasing velocity.
Which means that, wait, what?
So if you're always decreasing velocity, then your slopes are always decreasing. Or, you know, your tangent line slope is smaller. I don't know,
Okay, so he just says that your interval 1.4, 2 fails, so, like, right,
yeah, it doesn't dip down below.
so right, that's the only part that's wrong.
I mean, there's about